for the colored HOMFLY problem.
Okay, thank you so much for the invitation. It was a great workshop. I learned many things, and so actually there were a couple of talks about this subject already, but maybe from a slightly different angle. So I thought that my introduction will be very brief to the general circle of ideas around this, and so let me start by introducing the main characters of the story, and then the goal is to actually try to explain how you can compute things that we saw computed in various ways earlier from slightly different point of view, so using symplectic geometry. Okay, so the starting point is this UN Chern-Simons theory with a knot for a knot in S3. So there we have the level and the rank of the group, and we get these colored HOMFLY polynomials. So maybe HM of k is a function of little q and capital Q, where this little q is equal to e to the 2 pi I k plus n, and the capital Q is equal to little q to the power n. And the mth colored HOMFLY here is referring to the mth symmetric representation with m boxes like that. So, and then we can collect these things into some kind of wave function, which is a generating function for all of these. So, which I write like that. So it's just a way to collect these colored HOMFLY polynomials. And now, as we saw, there is a recent result by Gerfalides and company that says that this function, or these I don't know which one is which, but says that this function, the wave function, satisfies a finite differential equation. So that says that this colored HOMFLY is Q holonomic, but for our purposes it would be something of the following sort. So where these operators are, so p hat is right. So maybe I'll call this GS for string coupling constant. So then this would be GS ddx, and x hat is just multiplication by x. So and the main point is that this is a polynomial. So this is a polynomial in operators, right? So okay. So that's from the Chern-Simons side, and then there is a way to go into topological strings and holomorphic curves and all that thing, and basically it starts with Witten's result that says that this Chern-Simons is equal to topological string on the cotangent bundle of S3 with n branes on the S3 where the strings are allowed to begin and end. And then, so these are of course extremely brief, and I'm not saying anything about why, but then there is this Oguru-Waffa large n duality, which says that we can take this T star S3 with n zero sections over to, as n is getting large, this open string theory can become a closed string theory in the resolved conifold. So this is O minus 1. So we've heard this before, and this T is the area of CP1. Okay, so I should add a little bit more that when you have a knot, so I forgot, but when you have a knot in here, so when you have a knot as we have, then you should add here a Lagrangian brane on the conormal of the knot. So you take the knot and you take all the covectors that annihilates its tangent vector. That's what you have in here, and so here is also LK, and LK survives into here. So without sort of telling you much about this story, the outcome is that if you take a so this LK, I should say, is the conormal, so topologically it's just S1 times R2, and the S1 is corresponding to the knot, so I want to think of this X as some kind of homology generator. So if you count, and this is of course difficult to count, but let me anyway say what we're doing. So we count holomorphic curves which end on this LK inside inside capital X. So all the boundary components is on LK, and then you weight it as usual with minus the Euler characteristic, and then this Q is equal to e to the power t, if you wish. So that's kind of keeping track of the homology class of the curve inside here. And then you have how many times its boundary wraps around the homology of LK, right? So then we can define this difficult task, and I will tell you a little bit about how it's defined and so on. But imagine we can make sense out of such a count. Then this would be the open Gromov-Witten invariance of LK inside X, and the statement is that this duality says that this psi k of x is equal to e to the f of x. So where this you have this n times gs is q, so q is q here, where this is gs. Okay. So that's the starting point, and maybe kind of a little bit more of the starting point is that you can also now, once you see such expression, you can use some kind of shortwave asymptotics or WKB or whatever it's called. So you can write this wave function further as e to the of course f should depends on k. Otherwise it looks strange. So higher order terms. So now and this is you see they come in the order of the Euler characteristic. So this is the disk potential, and this is the annulus. And so what I will try to explain mainly, and that's somehow the starting point of this story that I want to tell, is how you can compute this disk potential from a theory called not contact homology, which basically is probing this geometry from infinity. So I'll say a few more words later, and I will also try to explain how how one can compute the annulus. And the annulus actually is better to maybe have two conormals, so one on one and one on the other. But basically, these two things is supposed to be also the ingredients that goes into this topological recursion. So there will also be a curve arising from this setup. So somehow all these ingredients are there. So I want to, and I think somehow maybe this we wrote about, but this one was not really explained. So I'll try to explain how that goes a little bit later in the talk. Okay.
This question about AK, should it be related to the Bachmann kernel on the spectral curve?
Yes. So it is somehow the appropriate replacement of the strict.
It's not precise.
It's not exactly the Bergman kernel, but it starts out like the Bergman kernel. But this is what should somehow be in place of yeah. You have to add a little bit, but then it should be what replaces the Bergman kernel in the recursion, indeed. Yes. So what about this not contact homology? So the idea, basic idea, is to look at this x. So basically, this is topologically well. So anyway, this is this O minus 1 over CP1. And if you go to infinity, you go very far from this CP1, then the x looks exactly more or less like the infinity of CP1 of T star S3. So at infinity, x looks like T star S3. So if you think in terms of symplectic geometry, there is on this space there is a symplectic form which is this dp dq, and here there is also input somehow from the symplectic area of this one, making it non-exact. But when you go really far out, then these perturbations becoming smaller and smaller. So you would somehow expect that if you look at holomorphic curves that live outside of very far from this CP1, then they look more or less exactly as they look in here at the outset. And the main point of all this business that I'm going to talk about is that at infinity in this space, we can actually do, in some sense, rigorous and easy holomorphic curve counts. And the next stage, and then those holomorphic curve counts come in sort of two flavors. One easier, and that we can actually do, which leads to what's known as not contact homology. And then the second one, which would involve higher genus curves, would be symplectic field theory, or maybe I should call it not symplectic field theory of knots or something like that. So that's, I would say, is work in progress, but there are somehow good guesses and some test cases have been worked out. So those are the two theories, and the not contact homology will give us. So the main input for this talk is that the not contact homology one gives the augmentation polynomial, which I will well, that's the polynomial. And indeed, it should be in a way, it should be the GS is equal to GS to 0 limit of this operator polynomial. It's not quite true. So if you know this guy, this one is, you can also compute, and then you find that when you take the limit, you get that one plus some junk. And I will explain why there is junk in this formula from this setup as well. So the 2 should actually now give, by similar means, so gives the operator so I want to try to explain this a little bit, and I want to also explain that there is a way not only to get the equation, but in fact not maybe so effective way, but at least there is a way to somehow genus by genus get at the wave function. And so in the second step we would get the annulus, so that's what I will try to explain. Okay. Very good. So let me first look at what is this not contact homology. So it's a part of what's called symplectic field theory, and related to all kinds of Floer homological theories in symplectic homology that we apply in this special case, when the Legendrian submanifold we're looking at is the conormal of a knot. So the starting point is not maybe LK, but lambda k. So we start with this lambda k inside the unit cotangent bundle of S3. Okay. And then the knot contact homology associates to such a Legendrian, associates an algebra, non-commutative algebra, over the group ring, maybe I'll use complex, of relative H2. And the generators are Rabe chords. So this is used in the contact structure here, and I won't say extremely much about what they are. In terms of a knot, if you have a knot K, then the Rabe chords are, so since we use the standard contact form here, then that's Rabe flow is just geodesic flow. So the Rabe chords are corresponds to somehow binormal chords beginning and ending on the knot. So oriented binormal chords. So you could see them in the picture. So this is some kind of generator. So this algebra, and there is a differential which counts holomorphic disks. So in other words, if and the holomorphic disks, they have the following form. I should say in this ST star symplectization of this thing with boundary on R times lambda k. So let me draw a picture, and then it should be clear what's going on. So basically, if I want to take the differential of a Rabe chord A, then what I count is I count holomorphic curves, which schematically looks like this. So at infinity, they're asymptotic to the Rabe chord A. So I pick my complex structure so that this R is paired with the Rabe direction. So it goes to A, and then it goes down, and in some sense it has finite energy when I project it down to the contact plane. And down at the bottom, I read off a word of Rabe chords. I should have used some other notation, doesn't matter, but I read off this word, so that would be an element in this algebra, free algebra. And then I keep track of the relative homology class of these disks, which gives me the coefficient. So in order to really kind of have it end up in this relative homology thing, I have to choose some capping data basically once and for all at each of the ends, but I can make it end up there. And note now that I should have said, so this, we can identify this H2, the relative H2. We can pick some generators. So this is just C e to the x. So this is the longitude class in the torus, the meridian class, and then the class of the fiber in ST star S2, which is, if you go to the conifold, exactly the class of the P1 in the middle. So we count rigid such. This means that this being rigid here, since everything is R invariant, means actually it has dimension 1. Okay, so this gives us some algebra, and the homology, for example, of this algebra is invariant under Legendrian isotopies of lambda k, and in particular under isotopies of k. So this is an interesting not invariant, and in fact, if you make the algebra even more non-commutative and say that this generator, forget about set q equals 1, so forget about this q, and then make these things not commute with everything, then in fact turns out this is complete not invariant. So it recovers the fundamental group of the complement with some information about the longitude meridian. Right. So it's pretty good, but here we want to do some kind of I mean, this is not so easy to deal with object, right? It's great that it knows something, but it's not so easy to deal with. So we are going to do the following. We are going to look at the locus in the coefficient space where we have a representation of this algebra into complex numbers, where we think of the complex numbers as equipped with the trivial differential. So we look for augmentations or chain maps epsilon, which takes our algebra into the complex numbers with the trivial differential. So as it turns out, the algebra is actually pretty simple from one point of view. So there are so the grading of a chord C is equal to the Morse grading of the binormal chord, the binormal geodesic. So this grading can be 0, or it can be 1, or it can be 2, but nothing else. So somehow here we want to have a degree preserving map into the complex numbers. So basically what we have to do is we have to, these you should think about as numerical values. And then for each degree 0 chord, we want to assign a number. And that should be our map. But the augmentation condition is that this is a chain map, so that epsilon composed with the differential is supposed to be equal to 0. So we define the augmentation variety to be the locus of this e to the x, e to the p, q, where there is augmentation. Augmentation epsilon exists. So let's see what it looks like algebraically. So I didn't tell you how to compute this differential, but from a braid presentation of the knot, you can get a kind of explicit form of this algebra. So we have a bunch of if it braids n times around the unknot, if you represent your knot like that, you can represent it so that it has roughly n squared or 2n squared degree 1 generators. And so we take this d of degree 1 generators. So that's a collection of polynomials. So the differential, I should have said, differential decreases degree by 1. Polynomials in degree 0 generators. So there are basically half as many degree 0 as degree 1. But what we see, so to understand what this is, you see, we have a large number of polynomials, and we need to find the locus where these polynomials have a common root. So this is some kind of statement about elimination theory. So in particular, this VK will be algebraic variety, and moreover, in fact, it is a it is a curve. So if you fix the Q, it is a curve. So there is a polynomial which gives this variety. So so it turns out this is one-dimensional, and we have the VK is in fact equal to some AK. And this is our augmentation polynomial. So that's how it's defined. And I would want to connect it up to this disk potential. So maybe one should do one example, because otherwise it's difficult. And it's always too simple example. And this is the example of the unknot. So, and I'm just gonna give the examples. So for the unknot, so there are two. So there is 1 degree is C, and degree C is equal to 1. It's one of degree 2, but we don't have to care about it. And there is no degree 0 generator. And one can see that there are 4 families of holomorphic disks. So the differential of this C is 1 minus e to the x minus e to the p plus q e to the x e to the p. And so in this case, there's a sort of no elimination theory to do, so there's nothing to eliminate, and this is just equal to the augmentation polynomial of the unknown. Okay. Very good. So now what I want to do is I want to try to connect this to the disk potential. And there is a story about this as follows. So the picture that we have is we have this lambda k, and then we have some kind of Lk filling the lambda k. And imagine first that there are no holomorphic curves at all forming on this Lk. So then we can define a chain map as follows. Namely, we take epsilon of A is counting rigid holomorphic disk on forming on this Lk. So it's somehow at infinity you have the Rave chord A again, and then stretching down is some rigid holomorphic curve, so that would be gives a count of things for each degree 0 chord, and I'm claiming this is an augmentation. Okay, so why is that? So that's because of the compactness theorem for holomorphic curves in this setup, which says that if I start with the differential, so I'm now starting with somehow C here, I get output chord A1, A2, A3. So this is D. And then I want to follow it by this epsilon. So I have to attach at the negative end, at each one I attach this epsilon count for the corresponding Rave chord. Then it turns out, so this is epsilon composed D, that this is in fact, I shouldn't use D again, so this is the boundary of the space of holomorphic disks of dimension 1. So this one became R invariant, so it flows off, and then somehow these are the only possible splittings in this case. So if there were no disk forming on this Lk, then I would get an augmentation by just counting rigid disks in here. So now there are disks forming, and that stops this argument, but the cure allows us to compute the disk potential. So let me try to explain that. So in order to see why, we need to follow this argument and see why it fails. So we start as before. So we start with this dimension is equal to 1 moduli space of holomorphic disk boundary on Lk, and then positive puncture at this C, I should see. And now it's almost, this is of course still boundary, but there are more boundaries. So what can happen is that as we go, and the only thing that can happen except for that is that an interior disk bubbles off at a certain time, and at this point, so this one is, I should say, this one is dimension 1. This one is dimension 1, and this one is dimension 0. So that's one of these disks that we would like to count in the Gromov-Witten potential, right? So we don't get the chain map equation, right? Because we would like to see that epsilon, D followed by epsilon is the boundary of some manifold, and it's not. But in this case, there is a kind of trick in Floer homology which was invented by Fukaya Ono, and it's called the bounding cochains. In this case, they're not quite bounding, but they're good enough. So imagine that, so somehow to cure this, we take this disk, this may be called D. So we take all these disks, but let's say this D, and this disk is forming on Lk, so it wraps some number of times around in its boundary. So we take a chain, just a topological chain, going off to infinity and connecting the boundary of this D to somehow k times x of the torus on the torus at infinity. Right? So here there is somehow, maybe I'll draw it in green, there is this meridian curve x, and my holomorphic curve, its boundary goes some number of times around the generator, and so I can find some chain going off to infinity and hitting the appropriate multiple of this generator of homology. So now, at this point, I can now continue and say that instead of just counting disks the way I counted them, I will count disks with that intersect these green bounding chains, right? So the idea here is that now this allows me to erase this from the boundary of the moduli space. So I split, but here I know which way I should go. It's somehow I should follow this disk in the direction of the green. It could also go the other way, but I don't go there. And so if I do so, I erase all my kind of boundary inside at the cost of counting not holomorphic disks as we see them, but counting holomorphic disks with insertions of these green guys everywhere. So in other words, my favorite equation is still true provided I put insertions of all the holomorphic curves inside, right? And of course I have to put the insertions everywhere. And I cannot guarantee that there are no insertions at infinity. But with these insertions, if I count appropriately, I should now have a chain map. So let's just look at what is the count at infinity. Well, at infinity, the count is extremely simple, because at infinity, all my holomorphic curves, whatever they look like inside, just looks like this kind of x curve or multiples of it. So in order to figure out, if I see a physical curve at infinity, if I want to figure out how many green, how can I, what does it contribute? I would have to just, let's do the count. So it should just depend on the homology class, right, of this disk in the boundary. So how many times, what is its homology class in terms of P? That tells you how many times it intersects the green, right? So the count is, first I would count 1. I insert nothing, right? And then I can insert one disk like this, so at one place, and that would be, so now if the count of disk, this potential, I write it as some kind of numbers. This should be maybe, okay, I'm suppressing the Q dependence. Q is living inside. C is a function of Q as well. So now, what do I have to do? Well, I claim that the next term in this sequence is somehow, when I insert one disk, I have to take the derivative with respect to K. So if it wraps K times around, I can wrap kind of, if it's P, I could insert it K times. So this is what happens. And then the next time I can insert 2 disks, and so on. So in effect, this is equal to E to the dwk dx. So if this wrapped once around, I should say. So if this was somehow in the class e to the p. So what this tells me is that if I make the substitution, so p is equal to the w dx, then I know I have an augmentation, right? So if p is equal to the w dx, then e to the x, e to the pq is inside this augmentation variety. So I have an analytic local parameterization of my polynomial. So now, of course, I can turn things around, and I can use this simple polynomial equation, for example, for the unknot. So then I can solve for you know, I could write it like this, something like that, and then P, which is the derivative of the disk potential of the unknot, is equal to the logarithm of 1 minus e to the x minus 1 minus q e to the x. Right? And I can power expand this, and then I get the count of holomorphic curves for any Lagrangian bounding this unknot. Right? So this is actually a calculation now of the Gromov-Witten disk potential. Okay. So I should say one more word, and that's somehow that once you see these green things, one should also realize that the disk potential also has to have these green things in its definition. So we cannot count. So somehow, if the boundaries link, then the count of these things should be, you count this disk, you count that disk, but you also count a disk which is like that, right? So somehow, and if for somehow the physicist in the audience, this is maybe a slight surprise, because what we're doing is, I don't know if it's surprising, but whatever we're doing just a model topological string with boundaries. So we write up some path integral, it localizes on holomorphic maps, so what's going on, right? But if you think about this path integral, you're integrating not over the space of closed curves, but open curves. And then there is boundary in this space, so there should be some boundary contribution, and I believe that this is the boundary contribution.
Again, what that picture, what the disk is in that picture?
Yeah, I should. So this is, I'm drawing the boundaries of two. So imagine I have a Lagrangian, which just have two holomorphic disks on it, and they happen to be linked, right? So then I want to ask, well, what should my Gromov-Witten count be? So I would like my Gromov-Witten count to be invariant, right? So if I change the j, it shouldn't change. So now, if I change the j, what can happen is these two could somehow come together at this point and then part. So when that happens, I would see these two disks, but I would also see somehow the gluing of them, right? So on this side, I count 3, and on that side, I count 2. So that's not so invariant. So now, how can I upgrade this to a count of 3? Well, what I'm saying is that we should actually count the two disks, and then we should count this one, which corresponds to linking. So here I would have a green. So maybe I make it life simple, and I take a green one on one of them, and there would be an intersection point here. So I'd have to count, you know, each disk separately and this disk with the other disk inserted. And then it would be 3 equals 3, and then somehow that's the thing. And but somehow you don't see, what I'm saying is that when you do some path integral proof of this, you don't see this immediately. This is not the holomorphic map, right? It's some kind of, it's two holomorphic maps, but it happens to
Is there a condition on that part that join the, I mean?
Yeah. I mean, in reality, this is, I have a big system. I take all disks, I take a bounding cochain, I go energy by energy. So this arc is actually corresponding to like an intersection of the boundary of one with the green guy of the other. So there is in general, it's a huge count, right? Okay. Okay, so good. So we determined this disk potential. So I will now try to say a word about what should be the generalization of this story and how it's supposed to work. So and I should say also that this is sort of not a simple generalization, but so I move now to this SFT first. So what we're supposed to do in SFT, we're supposed to replace these disks contributing to the differential by arbitrary curves. So it could have many positives, many negatives, some holes, and some further genus, all kind of holomorphic curves. Right? So, and maybe I won't really have time to tell you how this goes, but let's first assume that we can do such a thing, and we can also cure our main problem, which didn't quite disappear, so it's still here. So what we would like to have is we would like to have these specific one-dimensional moduli spaces, right, which splits in this way. No, these one-dimensional moduli splits in this way, so there is no kind of internal splitting. We have to cure all of it with a lot of green cycles. So what would we get? So we would get, in that case, by looking at the boundary of a one-dimensional moduli space we would get an equation which would look like this. So you take the count of these one-dimensional curves at infinity. So this is somehow these curves, all of them, at infinity. So that acts on our, I should say, e to the f twiddle now of x. And that should be the boundary of a moduli space. Maybe you want to put here, but it doesn't matter. We get an equation of this sort, where f of x now counts all holomorphic curves inside with and without extra punctures. So I should say what this counts. So f twiddle counts dimension equals 0 curves of the following form. So it could have positive punctures and then holes and whatnot, genus, and boundaries on LK, right? So in fact, I should have left a little bit of room, but we can write this f twiddle is equal to f twiddle 0 of x, where we count 0 positive punctures, plus f twiddle 1 of x plus and so on, where this is 1 positive 2, so on. And this is the guy we're after, right? E to the f0 should be the wave function. So we're pretty close, but we have too much here. And it's some kind of similar elimination problem that we're facing. But before I go into this elimination problem, let me show you what we would also have to do and what this green type argument with the bounding cochains leads to in this case. So, yes?
Since it's so natural to look at f tilde x, shouldn't the question be what does it correspond to on the kind of not theory side?
It's a great question. I don't know. I don't know yet. But indeed, it should. Of course, it itself maybe not completely in there, but it may be up to something, right? Because yeah, but indeed, I don't really know yet. But it should be. I mean, it's a sort of a counterpart of an augmentation in higher genus stuff, right? Whatever it means. But now we're going to the deformation of the augmentation, which is in some sense. Okay. Right. Yes. So let's see where this green stuff leads us. So imagine still that, like for the unknot. So unknot is unfortunately erased, but unknot is an example where at infinity there are only disks, right? So let's look at the unknot. There are only disks, and we want to cure this splitting of things. And we know that we have to do some curing, right? So before we had some maybe holomorphic disk, and it was inserted somewhere, right? So now let's see what will this setup lead us to. So we learned last time that we had to put this p is equal to the w dx. But now when we count higher genus things, there is a difference. Namely, we can take this thing and we can insert it not only once. If there are two such things, we can insert it twice, right? And that would give you something with a genus, right? So you glue it once, one more. So let's try to do the count. So first again, so let's say this is e to the p, it wraps around once. Again, at infinity, everything looks like this x, so it's really simple. So first we count our thing, that's 1. And then we count all the curves in here. Let's say in this case, there are no positive punctures. So we count 1 insertion, right? And then the next time we count 2 insertions. And of course, again, we can take 2 different curves in the count and insert them twice. But we also have the possibility of inserting 1 curve twice, right? And then now you go on like this, and you see that what is the result? The result is e to the gs ddx e to the f, right? So the previously we made this substitution, but now we should put p equals to gs ddx. So this is our enumerative interpretation of this quantization, and indeed, we see that this begins pretty well. So this age should have, in order for such a thing to make sense, we should put p is equal to gs ddx. So in particular, in the case when you have no extra these negative punctures, we solved our problem, right? For the unknot, for example, we found immediate quantization of this curve, and so again. So this was just 1 minus e to the x minus e to the p plus q e to the x e to the p. And to solve it, we just put somehow operator everywhere, and that's the quantized curve for that. I mean, this is somehow baby example because it's linear, but anyway, so here we see how it works. Now in general, and I'm not going to talk about general so much, it's there is a kind of a problem that this equation will involve these extra degree 0 punctures, which were before also there. When we did it commutative, we do ordinary elimination theory. Now we have to do elimination theory in the coefficient ring of these operators. So it's a little bit more delicate, and so that's one of the points which I won't explain properly, but I can at least mention that when you do elimination theory, you find something with multiplied by something else. So this f times something and g times the same thing in the other equation. You multiply by g here and f here, and that's fine. But in non-commutative, you gain some factors, and they turn up in this story. Okay, but let me stop at that, and now let me tell you just very briefly how one would go about calculating this annulus amplitude. Okay, so yeah, the starting point, so annulus. So let's take a link. So let's take L, which is equal to K1 union K2 in S3. And now we want to count annuli between LK1 and LK2 in X. Okay, so then there are a couple of lemmas, but the main lemma is the following: that if you when you have an augmentation, allows you to linearize the algebra AK and the differential, and you get some kind of linearized homology. So maybe I call it contact homology linearized. of k. I want to put k. Okay, and and it turns out that for I mean, so we don't really know that this curve that we're working over is irreducible, but imagine for a while that it is. So we know that for small q, we can actually calculate this linearized homology for generic point in the curve from just the calculation in T star S3. And that calculation gives you that this is generically equal to, well, rank, maybe I put rank. Is rank 1 in dimension equal 1 and 0 in dimension equal 0. So this is dimension or grading. Okay, so this allows us to calculate the annulus amplitude inductively from knowing all the curves at infinity. So I want to just, and in fact the whole wave function. So let me first just show you what's the essence of this argument, and then I'll try to do the hop link. So basically what we want to do is we want to take this moduli space. So one boundary is on LK1 and one is on LK2. And here we take the generator of this linearized homology. And so we look at the boundary of this moduli space. And what is it? Again, we have used the augmentation disks and all these things to cure all the boundary splitting. So what it will become is that it can split like this. And then it can split like this. And then it can split like this. So you take the disk at infinity and then you insert in the interior one annulus. So this is the guy that we want. That's what we want to compute. But the fact that this C, we take it as a generator of the linearized homology, means that the count of such things is 0. So that goes. And so we're left with computing this one, which we can do at infinity, and this one, which is in the inside. So this one is rigid. But the fact that we now have this degree 0 linearized homology means that we can find a primitive B of this A1, for example. And this is the boundary. So this plus the one at infinity are invariant with B A2. That's equal to 0. And this guy we can easily count at infinity. So, so the upshot is that we can solve, I should say that this one also, the count of this one is divided by the augmentation polynomial. Likely it is always the augmentation polynomial. So you have to take the derivative of the augmentation polynomial with respect to p, and that's the coefficient of the annulus here, and then you have to do some calculation. So let me maybe show this in this one example, which is not so hard. So okay. So let's look at the hop link. So we just have this link, and then we first need to do the actual count. So here I take kind of this is x1 and this is x2. So but for the meridian and longitude classes. So somehow first you can do this. I don't know. You can do it in many ways. You can do Chern-Simons, or for those who really like to count curves, you can count curves in T star S1 with a shifted zero section or something like that. But the count of curves here is logarithm of 1 minus e to the x1 over e to the x2. Or maybe better. So it should be, yeah, x. So the one that is usually x1 here, that would be some count like that. But the p2 is the x2 when you do the HOMFLY. So okay. So this is the count of annuli. And now what we're really interested in is somehow is the second derivative of this thing when you take derivative with respect to both to x1 and x2 or something like that. So it's not completely canonical the way I write it. Okay. Okay. So that's equal to well, and e to the p2 is given by the augmentation polynomial of the unknown because we're in the augmentation variety. So that's the thing that you get from true counting. So let's do this indirect counting that I wanted to do. So yeah, I should. I'll be happy to show. It's not so hard to actually draw the pictures that gives all these curves counts that I'm going to give you, but let me not. Let me just write it up. So here there is this guy is our main thing. We call it C11, and this C11 count is given by the one that you would think. So that's exactly the same count as for the Lagrangian of the unknown. That's one. And the second count we have to do is this triangle count. So I should say there are two. So yeah, there are somehow two A12, A21 short chords, and this A12, A21 is the count is just one. Oops. And 3, I want to count, I need to count this primitive, so it's somehow C21, A12, and the count is 1 minus e to the x1, e to the p1, e to the minus p2. And finally, this primitive to 1. And here you have q e to the x1, e to the p1, minus e to the p1, e to the minus p2. So that somehow is the counts that you do. And as you see, somehow so I should have shown you, but I'll show those interested that these things, the counts that I'm doing here, you can do just by pictures. You draw a kind of a square, a torus, you draw some discs, and then the braiding of this braid, and then you can count all these things. And when you do my calculation that we have here, then actually after, so you have to, if you want to do it, then you have to set I think e to the x1 replaced by q e to the x1, and then you're fine. Then you get this form for the annulus. So I'll stop at this. I should maybe just mention before I stop that there is nothing very specific about the HOMFLY link here. This is a rather easy calculation for any link from what we did already for calculating all the disks with negative puncture. So the only thing not in that expression is this disk, but it's calculated in more or less exactly the same way. So we haven't written that anywhere, but it's somehow easy to figure out what it should be. Okay, I'll stop at this.
Questions?
Yes.
Okay, so then is the hope that you can then do all the rest by topological recursion with this initial data?
Yeah, right. So formally you can, once you have the theory working, you can do it, right? Because now imagine that you want to go further in topological recursion. Everything before was determined. So then instead of this one, I put here some kind of Euler characteristic. And then this guy is still gone, which will have Euler characteristic same here. But see, in all the rest of the splittings that you see, this guy is the one that you're interested in. And then in all the other splittings, it could be more complicated, I don't know, but in all the other splittings, everything has lower or higher or whatever it is, Euler characteristic than in the step before. So basically, this is a proof of a version of topological recursion that would construct for you the wave function. So this works in some sense, but it's getting complicated, right? The good thing with this thing is that at infinity you can make sure there are no higher genus, no actual higher genus curves. So all of it will be disks with several positive punctures and maybe some linking information. But basically this is showing that the solution to the thing exists in some sense. So but the topological recursion I'm talking about is something different. So the topological recursion I'm talking about is somehow, applying topological recursion, or that the annulus is related to. That's doing topological recursion on this curve with this kind of P is the W dx. So then I have this P dx differential, and then you need the Bergman kernel, the annulus, which would be, I think, now kind of this D1, D2, A, and then I think you have to, add some standard piece like this. And it's plus or minus, I don't know, but this should be the ingredients of topological recursion. And the conjecture in that business is that if you follow this in our Antin recursion, then you in some other way reconstruct this e to the f, right? It's a B mod.
It's not a recursion on the free energies. Usual topological recursion is not a recursion on the free.
That's right. So, the conjecture would be that the usual topological recursion constructs in the B model way for you this kind of e to the f. That should be the wave function of this guy. He constructed in a different way, right? So my recursion is different. It also constructs e to the f.
More directly on f.
It's more direct. This is an A side thing, and it's very hard to see actually. If you know this, why you don't know this, or at least I don't know this. So okay, I don't know. One has to. I don't know also about this. Maybe it's true. Maybe it's not true. I think something like this is definitely true, but the curve A is not so smooth. So there could be some singularities. Maybe I don't know. Yeah.
As a small comment, I think Albrecht Glenn has some paper where they try to guess what is this like Bergman kernel thing for some simple nodes to reproduce correct result. So I'm not sure if you saw.
Yeah, I saw it, but so for the hop we agree. But beyond for the trefoil it should probably also be the same if you do the right push, because there we have the whole recursion relation, so it should all be compatible, I think. But beyond Hopf and trefoil we haven't actually gone further. Mainly because of problems with this SFT theory, but it's so yeah. The last trefoil calculation is somehow giving more confidence to this the SFT business. Yes.
So, the ultimate goal is somehow to compute this A hat operator, and do you understand what information in what sort of holomorphic curve information you need to?
Yeah, pretty much. So for example, for HOMFLY and for trefoil knot, we actually did it in some sense. So, and what you need to know is you need to know if you set it up right, you basically you have to look at some curves with one positive degree 1 thing and all the rest degree 0, and that should be the physical curves, the disks. They are only disks if you set it up right, and they can be determined from a braid presentation. So then you need to also figure out a bit of this. If you have two such things, how they link or how they intersect. So that corresponds to this green insertion or something like that. So those two things together should give you the age, right? And then you have to do this non-commutative elimination theory, and whether one can do this systematically, or well, probably one can, but I don't know any theory of this. But basically, that should hold the information. And so I think, I mean, in the best of worlds, you get this before the elimination. You get it actually from a braid. I think we should be able to get something like that. You draw it as a braid and braid word, and then you should get the age. And then to eliminate, that's yeah, a hard story. Yeah.
Okay. And so you can explicitly work out what these counts are.
Yeah. For if you have a knot that you're very interested or linked, then I could do it. Yeah. Yeah, that's right. But I think there's even hope for some kind of formula. I think, which may be big, but anyway.
One more question about this topological recursion. So you hope to use it to reproduce wave function. So then you would use this open WGN invariance and hook up to the wave function somehow. But the recursion also computes this closed, like symplectic invariance.
Yeah.
And what would be those from your perspective?
Yeah, from my perspective, those would be, so that's why I'm not completely sure also about this. No, from my perspective, the closed thing should just be the count of curves in the conifold again, right? So this is somehow.
It doesn't depend on a knot.
It doesn't depend on a knot, suppose.
Get the
I
same
mean,
answer
Clem checked it explicitly in the paper you mentioned.
It should not depend on a knot.
Cover the ordinary closed string count contours.
It's a B model. It's a weird B model calculation of what's happening in the conifold. Should be.
Masochistic B model calculation.
That's right. so right. But somehow when you draw the usual picture, you can kind of believe that this is the case. But here it's less. I wouldn't know how to, see it in some sense from this. So given that you can see all these things, annuli, so why it concentrates, I don't know actually. But that's what it's supposed to be. Yeah. Yeah.
And then so, sorry, let's make sure I understand. So supposing you have a hat.
Yeah.
This is the subject of Piotr's talk yesterday.
Yes.
Can I, if I know a hat, can I then recover, and say I wanted to calculate all the colored HOMFLY polynomials?
Yeah.
Would it be enough to know a hat, or do I need?
No, I don't know. I mean, I'm not sophisticated. I would have to know this one and some initial conditions, and maybe you can say something about limits. So you know something about classical limits of this one, because if you take Q to 1, then you see, say, maybe the conormal feeling or some other feelings. You can say that P goes to 0 or something. So you know something a little bit, but I don't see any way. If you have a very complicated knot with a really long recursion, I don't really see how to. I would need some initial data to kind of how to determine. I don't know actually. Yeah, but I mean, of course, in some sense, maybe this is helpful, but. But I haven't really. Yeah.
All right. Well, thank Tobias again.